Okay, we are recording now.
Okay.
Okay, so first of all, thank you for the members of the committee, Don Tausley and Geraldo Chechel, and I guess the word to Mariana to start the presentation, and after that we ask questions, and then there will be a little bit of little formality at the end, the very end. But after the questions, we talk about it. Okay, Mariana, up to you.
Okay. Good afternoon, everyone. My name is Mariana Corrêa Ribeiro, and today I will present my work that is called A Study of the Impact of COVID-19 Pandemic on Residential Network Traffic. I want to make a special thanks to the committee members for being present today, and also to my advisor for always being by my side, guiding me on this journey. I also want to especially thank my professor Rosa for all the support and teachings that she gave me, and my friend Ananda for her partnership and for helping me during these years of work. And finally, I want to thank everyone here, all my friends and family. So, the COVID 19 pandemic was an unusual event that has changed the daily behavior of populations around the world since the implementation of social distancing policies. The social distancing policies have affected people mobility patterns and internet traffic, increasing the volume of traffic around the world. Due to this increase in traffic volume, video platforms like Netflix and YouTube lowered the quality of videos to reduce the network overload. These sudden and unprecedented changes in the traffic patterns have affected the quality of service perceived by users around the world. But why is it important to study anomalous traffic events? Because it's relevant to understand the impact of a large magnitude event that causes an anomaly in traffic patterns, with the objective to improve future traffic management and planning on the internet network. The objective of this work is to answer three questions. What changes took place in residential traffic patterns after quarantine policies were adopted? What changes haven't taken place in residential traffic after the relaxation of quarantine measurements? And would it be possible to correlate mobility measures with residential traffic patterns? The main contributions of this study are a methodology that allows analysis of anomalous events of residential traffic patterns, an analysis of the residential traffic patterns and the impact of quarantine on these patterns, instance of time where occur changes in residential traffic patterns due to quarantine, and determine if there is any relationship between residential traffic patterns and Google mobility data. The main difference from our work to the related works are we do not do deep pack inspection, and some works analyze the traffic changes of application classes through deep pack inspection and or consider predetermined patterns to characterize the traffic flow. Unlike other works, our focus is on analyzing the traffic patterns of the residences and not the total traffic at certain points in the network obtained on non-residential routers. That is, routers that are in the middle of the network, which are not residential routers. And we use unsupervised analysis to discover residential traffic patterns. Because we only have the traffic data of residents per minute, we use an unsupervised approach to try to find patterns in this residential traffic. And our measurements are performed on the user's home router per minute. Many works make an analysis of the total traffic obtained in non-residential routers. And in addition, our data set was collected with granularity of 1 minute. Generally, collections are done at intervals greater than 5 minutes. And to do our data collection, we partnership with Jiggly, which is a medium science service provider, an ISP, located in the state of Rio de Janeiro. And we participate in a cooperative research project that includes the ISP and NLIX, that is a startup incubed at the university. So the ISP runs the software developed by the startup inside the home router to collect and send information of the devices connected on the router to the server. And the software inside the home router include collections of metrics obtained through active and passive measurement. So basically, the home routers collect measurements from the devices and send via internet to the server to be stored. And our data set is composed by download and upload bit counters at every minute. It is anonymous and does not include any sensitive user or provider information. We have more than 5,000 residential routers spread across 15 cities in Rio de Janeiro state, and the measurements were taken over a period of almost 2 years. Because the pandemic affected the way users use the internet, we did an exploratory and preliminary analysis of our dataset to understand if our data has also changed due to the COVID-19 pandemic. And we think that study and understand what happened during the pandemic is of paramount importance to be more prepared for future events. So with that in mind, we perform a simple analysis on the traffic volume using download and upload data of residential routers. And our objective is to understand if there was any change in the volume of traffic of our data during the quarantine in Rio de Janeiro state, which started on March 16, 2020. So this image here represents the upload traffic of a residence for one day, 1,440 minutes. And we want to understand if there has been a change in our residential traffic during COVID-19, as seen in other traffic measurements around the world. So during the pandemic, users use many applications that require high upload and or download rates, such as watching videos and participating in video conferences. And because of that, to differentiate applications that use high upload and or download rates like Teams, YouTube, and Netflix, of applications that require low rates like email and browser, we need to define a threshold of the minimum required rate for an application to be considered an application that uses high upload and or download rates. So to do that, we analyze the speed requirements of upload and download rates in the applications most used by users in the world to watch videos and to participate in a video conference. And we exemplify some of them in the chart. So the minimum required rate to watch a video in YouTube is 70 kilobits per second. And the minimum required rate to do a video conference on Teams using audio and video is 1.5 megabits per second. And the minimum required rate to watch a video on Netflix is 3 megabits per second. So to be more conservative, we define at 50 kilobits per second the minimum required upload and or download rate for an application to be considered an application that uses high traffic rates, which is our threshold. And an important thing to say is that we don't have the labels of the classes of the applications, that we are defining this threshold. Another important thing to say is that it's not the objective of this work to differentiate the classes of applications. This analysis is just an exploratory and preliminary analysis of our dataset to understand if there were changes in the traffic. And again, we don't have labels, so we define a threshold. What we want is the average number of minutes that a resident spends above a threshold value during the pre and post quarantine period, which starts on March 16, 2020 in Rio de Janeiro state. So this image is also represent the upload traffic of a residence for one day. And you can see that most of the time, this residence uses rates below the threshold. And once this residence passes this limit value and has these peaks, it's most likely this residence is using applications that require great amount of upload data. And what we want is to compare the number of minutes a resident spends above the threshold before and after the start of the pandemic, in order to understand either these residences are using more applications that require high upload and or download rates after quarantine started. So we illustrate the expected number of minutes above a threshold per day before and after the quarantine for upload and download rates. And these red line here represent the linear regression of the pre in black and post in blue quarantine periods. And if we compare before and after the quarantine, there was a 50% increase in upload rate and 33% increase in download rate during the beginning of the quarantine. And these increases happened in a matter of days. There was also a small increase in early 2021 in both figures, which may have occurred due to the second wave of COVID in Brazil. And you should note that linear regression for both figures indicates that over time, the expected number of minutes above a threshold decreases after the beginning of the quarantine. So we conclude that there was a significant increase in the time that users stay connected and use applications that require high traffic rates during the beginning of the COVID-19 pandemic. However, if we follow this average over time, there was a practically linear decrease. And with these conclusions in mind, we began a deeper analysis in relation to the traffic data. And now we're going to present an overview of our traffic patterns methodology, and then we're going to explain it in more detail. So we use a 5-week training set from the year 2019 and create a tensor. And after retaining this tensor, we use the factor analysis algorithm called PARAFACT to decompose this tensor and obtain the loadings. And this PARAFACT model here will be called our reference model. The loadings obtained in PARAFACT were used as an input to the clustering algorithm called hierarchical clustering in order to separate the data, these loadings, into clusters with similar patterns. So basically, we got this data, these loadings, that we don't know what they represent, and we want to understand if the data follows any pattern. And if they do, can we separate them into clusters, into groups? The profiles or clusters obtained with the clustering algorithm were used as an input of a classifier called decision tree. And the objective of this step is to train the classifier with 2019 data and classifying the new data. And this step was made so that we don't need to run this whole model again every time we want to classify a new data. So after training the classifier, we build another tensor with the new data from 2020 to 2022. And then we calculate the new loadings of the new data using the PARAFACT reference model with that was trained with the data from 2019. Next, we use this classifier already trained with 2019 data to classify this new data. And finally, the new data is classified into groups of residential traffic called residential traffic profiles. So now we're going to explain the methodology in a more detail. And we use a 5-week training set from the year 2019 and create a tensor. But what is a tensor? A tensor is a multi-dimension array, and we use a tensor because we are working with multi-dimension data. We have a set of residents with download and upload measurements by the minute, so we separate the time series of each residence into daily samples. We define X as a 3-mode tensor, IJK, where the I mode identifies a single and anonymous residence on a given day. We call it residence day or pair RD. The J mode identifies the minutes in an interval of 1 day. and the K metric represents the download and upload bitrate per minute. The tensor of the 5-week training set from the year 2019 will be used as an input data of the factor analysis called PARAFAC. And PARAFAC is a method that decomposes a tensor into a set of factors, latent variables, and loadings. Basically, it's a method that reduces the dimensionality of multidimensional data. And our objective with this method is to represent the data in a simpler and more compact way, which can make the model easier to interpret. The equation of the PARAFAC for a tensor X of order 3 is defined below. And the tensor X with 3 dimensions, ijk, represents the data. R is the number of factors. So in this graphical example, we have 5 factors here. And A, B, and C are the loadings of the factor R corresponding to each dimension. So A represents residence day, B represents minutes, and C represents the metrics, upload or download. And E are the residuals, which represent the data that the model cannot explain. Basically, PARAFAC calculates the loadings that minimize the sum of the squares of the residuals. And as a result of the PARAFAC using the 2019 data, we got a 5-factor model. And this figure represents the loadings for each minute and for each of the 5 factors during a 24-hour interval. And you can see that in this figure, we are already giving labels to the factors obtained, and the duration of each of these factors can be inferred from the factor weights here. So for example, the morning factor peaks at approximately 9 a.m. So we call it morning factor. And the night factor peaks at approximately 9 p.m. So we call it night, and so on. And we obtain this base factor here, whose weight is approximately constant through the day, which is probably related to the relative low bit rates through the day. And after obtaining the loadings using the PARAFAC, we use the same loading as an input for the hierarchical clustering to obtain the clusters, called by us profiles. So the agglomerative hierarchical clustering defines groups of objects based on their similarity. And the objective is to group this time series that have similar temporal features. Basically, what we want is to know if these loadings obtained the PARAFAC have patterns. And if they do, can we separate them into groups, into clusters? The algorithm uses a bottom-up approach, so it basically starts by treating each object as a cluster of its own. Then pairs of similar clusters are successively merged until all objects belong to a single cluster. When we apply the hierarchical clustering in the data of 2019, 3 residential profiles were found. And in these figures, we represent the median of download and upload traffic per minute for each profile. So profile A in purple represents residents that generate high traffic rates during the day from 9 a.m. to 2 a.m. Profile B in green represents residents that generate low traffic rate all day. And profile C in orange represents residents that generate high traffic rates at night from 6 p.m. to midnight. And after obtaining the clusters or profiles, we use the PARAFAC loadings and the clusters to train a classifier called decision tree. So decision tree is a supervised learning algorithm, and it's used to solve regression and classification problems. The objective with this method is to train a classifier with 2019 data and facilitate the classification of the new data of 2020 to 2022 using loadings and clusters. The training algorithm builds the tree recursively from top to bottom. So basically, it starts by classifying at the root node of the tree. Then it passes to a decision node, and then when a leaf is eventually found, the data is classified into a class. After creating the classifier, we generate a tensor with the new data of 2020 to 2022. And after generating this tensor with this new data, we use it as an input to the PowerFact reference model to calculate the new loadings of this new data. And after obtaining these new loadings, we use the classifier already trained to classify this new data. And now we're going to show the results that we obtain with this classification. So this figure represents the time evolution of residential profiles, and it illustrates the daily percentage of each profile. The x-axis represents the days. The y-axis represents the percentage of fractions of residents per profile. And the state of Rio de Janeiro issued social isolation measures on March 16, 2020. That is the day of the beginning of the quarantine, and all cities in the state were affected. Until the first phase of relaxation measures that starts on June 2, 2020, all non-essential commercial and educational establishments were closed. In 2021, due to the increase in deaths from COVID, the governor of the state of Rio decreed a one-week holiday on March 26 to April 4 in order to contain the spread of the virus. The horizontal blue line showed the fraction of profile A 1 week before the quarantine, that was on March 9, 2020, and 12.9% of the residents were associated with profile A. That is the profile characterized with high traffic all day in purple. Just 2 weeks later, on March 23, the percentage of the profile characterized with intense use of internet more than doubled. Weeks later, profile A showed a downward trend until 2021, when it slowly increased again. Profile C, that is the profile characterized with high internet use at 9 in orange, behaved similar to profile A during 2020 to 2022. And profile B, that is the profile characterized with low traffic all day in green, during the beginning of the quarantine, decreases 36%. These results show how residents move from one traffic profile to another after quarantine. And the fraction of residences that belong to profile A, that is the profile characterized with high traffic all day, was constantly decreasing during 2020 after March 23. And the different restriction policies did not have a significant impact on internet use. Next, we calculate the average of the daily fraction of each profile for periods of 4 weeks before and after the quarantine. And we're going to call it the pre-quarantine 4-week period, the reference period. And this reference period is not represented in the chart. So we have 24 subsequent 4-week post-quarantine periods that are referenced in the figure as week 5 to week 8 until week 97 to week 100. Basically, this graph represents the percentage difference from the pre and the post-quarantine periods. And the greater the positive or negative distance from 0, the greater the difference in relation to the pre-quarantine period. For example, in the first period here, we have profile A that increases almost 13%, which means that 13% of the residences migrated to profile A. And there was a 15% decrease in profile B, which means that 15% of residents migrated from profile B to profile A or C. And if we compare the period right after the beginning of the quarantine with the period that represents the end of 2020, it seems that the percentage of the profiles were getting smaller. That is, they are getting closer to the percentage of the pre-quarantine period. These results indicate that as residents were slowly returning to their reference periods, that is the pre-quarantine period. And at the beginning of 2021, the residentials changed their profile again, and the percentage started to increase, which coincided with the beginning of the new wave of COVID in the state of Rio. And this change occurred even though no additional isolation measures were taken. The third wave of COVID in Brazil started in early 2022, and in this period, the trend of the three profiles changed again. In the following, we compare the evolutions of profiles in different cities. This chart presents similar metrics to the previous chart, but we only illustrate the four most populous cities in our dataset. And in the subtitle here, we have this pop size here. That means for each Brazilian city, there is a known city in the world with similar population number. So for example, Niterói has a similar population size as Miami in US. And if we compare the cities, we can see that they follow a similar trend. The tendency at first was to change profiles, then they returned to their percentage of pre-quarantine levels. In 2021, the percentage of each profile started to increase again, and it decreases after the second wave of COVID in Brazil, as well as in the previous chart. Interesting, in weeks 93 to 96, the city of Nova Friburgo practically returned to their pre-quarantine levels. That is, the percentage of residents of each profile became close to the values of the reference period. These results show that despite being quite different cities, they followed a similar pattern. In our next analysis, we want to formally identify the instance of change in the distributions of the residents by profiles. That is, when the changes in the percentage of the number of residents between the residential profiles occur, using a frequentist approach. And the objective of this analysis is to find the correlations of possible instances of change with events related to social isolation policies. We use maximum likelihood estimators in order to identify instances where changes occur in the percentage of residences in each profile. So to construct our model, we are assuming that the total number of residents is very large, that n samples are drawn per profile, that the probability of drawing a residence belonging to a given profile is constant until we detect a point of change, and that we have a binomial distribution for each profile. So assuming that I have a population that has three profiles and that the total number of residents is very large, and that we don't know the average of this total population, meaning we don't know the fraction of residents in each profile, I have to sample from this total population as an election poll. And when I sample, I obtain the mean of the fraction of residences per profile. So the model is the probability of sampling a given profile. And our model is binomial for each profile. So when I sample for the total number of residents for each day, I obtain the mean of each profile. And when the mean change, I detect a point of change. So in this example, from the total number of residents, we sample over 3 days. And we get the daily average per profile. Then we compare the daily average and see if they change. If they do change, we detect an instant of change. The blue line here represents the days I'm sampling. And in this case, in this example, is 12 days. And for each profile, the sampling, the day, I check the mean of this profile. And when this mean change, here, in this day 6, is where I detect the point of change. So the model parameters will change too, and in this case is the mean of the profile. The model is defined below, and this figure illustrates the instance of change for profile A, which was the profile characterized with high traffic day rate all day. And the point in red and the line is in blue represents the same thing, but to make the trend of the posteriors clear, we added the line. The x-axis represents the days that the instance of change occur. The y-axis represents the probability that an instant of change occur on a given date, named as posterior. And to generate this image, we apply a filter. That is, the probability of a given day being an instant of change must be greater than 80%. And at the beginning of the quarantine, that was on March 16, 2020, 3 instances of change were presented on March 15, March 17, and March 20. And the most likely day among them to be the instant of change was March 20. In 2021, the most likely periods of change were May 3, the period after the second wave of COVID in Brazil, and November 2, the end of the year. In profile E, that is the profile characterized with low traffic all day, at the beginning of the quarantine, the most likely day of change was March 16, 2020. That is the day of the beginning of the quarantine. And in 2021, the most likely instant of change was in the beginning of the year, in January 1st, which coincided with the start of the second wave of COVID in Brazil. Profile C did not present an instant of change right after the beginning of the quarantine. You can see that February 25 is 1 month before the quarantine started, and April 19 is 1 month after the quarantine started. So this is an indication that there were no major changes in this profile. With this analysis, we conclude that a significant fraction of residences migrated from the traffic profile characterized by low internet use, profile B, to the profile characterized by high internet use through the day, profile A. However, almost no change occurred in the profile of high internet use at night, profile C. And in our next analysis, we're going to talk about the adherence of the residents in relation to quarantine. And the objective is to infer either changes in the traffic behavior are related to population adherence to quarantine. We use Google mobility data that shows movement trends over time by category, work and home locations, and regions, country, states, and cities from users' cell phones during the COVID-19 pandemic. Google calculates the relative change that is defined in this equation, and we use the same equation to calculate our metrics, but we use a fraction of residences. What we want with this analysis is to find the correlation between the relative change metrics of residential locations and work locations estimated by Google with the relative change metrics we calculated from the residential traffic profiles. So this figure refers only for the city of Nobre Friburgo, and it shows the 7-day exponentially weighted moving average of the relative change of the variables estimated by Google and the variables estimated by us. And we compare the time people spend in their residences with the fraction of residents associated with profile A, which is the profile characterized with high traffic all day. The red dashed line here marked the beginning of the quarantine on March 16, 2020. And we can see that after the quarantine starting date, both graphs show a sudden change. The graph indicates that as quarantine relaxation measures were implemented, people began to leave more often and return to work. Consequently, the fraction of residents associated with intense internet use decreases. Next, this figure shows the 7-day exponentially weighted moving average for the time people spend in their workplaces with the fractions of residents associated with profiles jointly considered B and C. The graph also indicates that as quarantine relaxation measures were implemented, the number of people returning to workplaces increases, together with the fraction of residences in the profiles jointly considered B and C, confirming that residences were returning to workplaces and going out more. And in Brazil, there was never a quarantine like in Europe or US, meaning that people were never forbidden to live in their residences. People didn't go out because of the fear of contracting the virus. And most likely, they were induced to stay at home because of the news on TV or on the internet. And due to the similarity of the previous figure, we use Pearson correlation coefficient to calculate the correlation between the 7-day exponentially weighted moving averages. And this table shows the results for the four most populous cities in our data set. And the results demonstrate a strong correlation between our metrics and Google mobility metrics. But the question we are left asking is, does this strong correlation really indicate that people are at home? To answer this question, we analyze the Wi-Fi data from the residence of the users. And our objective is to understand if the increase in residential traffic and consequently in the number of residents in profile A, which is the profile characterized with high traffic all day, can be an indication of the permanence of users at home. So we use an assumption that if the cell phone is connected to the home router, the user will be at home, because people don't often leave their homes without their cell phones. And our data collection is the number of download and upload bits per minute, and we only collect data from cell phones when they are connected to the home network. Otherwise, the measurement does not exist in our database. We consider the number of minutes that a user's cell phones were connected to the Wi-Fi network between 8 a.m. and 5 p.m., that is standing working hours, to see if the number of users at home has increased after the quarantine. So this figure represents the average minutes between 8 a.m. and 5 p.m. by cell phone per residence per day. And the three dotted lines here represent the average number of minutes per cell phone per residence on March 9, March 16, the day of the beginning of the quarantine, and March 23, 2020. The yellow area corresponds to Carnival in 2020, and the gray area characterized the post-quarantine period from 2020 to 2022. The average number of minutes per cell phone per residence between March 9, 1 week before quarantine, and March 23, 1 week after quarantine, increases by 44%, and after this period remain almost constant. In addition, the average number of minutes per cell phone per residence in the pre-quarantine period on white is 13% lower than the post-quarantine period in gray. And these results show that the increase in cell phone traffic on residential networks increases the probability that users are at home using their local network. This analysis corroborates the relationship between the increase in residential traffic and Google's mobility data. In summary, our findings were: we identified 3 distinct residential traffic profiles, and we showed that a significant percentage of residents changed their profile after the quarantine. So a significant percentage of residents switched the profile characterized by intense internet use, profile A, and this behavior was similarly seen when we analyzed the 4 most populous cities in our data set. And it's important to note that these are not traffic volumes, but residential traffic profiles. Using a frequentist approach, we identify the instance of change in the distributions of the residents by the profiles, and that there was a significant change in the fraction of residents associated with the profile characterized with intense internet use all day, and the profile characterized with low internet use all day during the beginning of the quarantine. We found a strong correlation between the changes in residential profiles obtained by the model with Google mobility data. Profiles can be a parameter to estimate the effectiveness of isolation measures in the population of the region without using users' privacy data, even if people have not been forced to stay at home. And we calculate the average number of cell phones connected per home router during work hours between 8 a.m. and 5 p.m. And this analysis corroborates the relationship between the increase in residential traffic and mobility data. We conclude that the residential traffic patterns or profiles show that they can be a metric to estimate either the user is at home or not using a few residential traffic information. And this is important for the management and planning of the network. About our publications, we published an article at the Brazilian Symposium on Computer Networks and Distributed Systems in 2021, and we won an honorable mention. And we are writing a journal called Residential Traffic Profiles, what we could learn from the lightweight measurements during the pandemic. Thank you.
So thanks a lot, Mariana, for the presentation. And,
deixa eu interromper um minuto por causa da gravação. Eu acho que eu vou parar a gravação e começar de novo, tá? Pra gente ter os bloquinhos separados, porque a gente só bota no site a apresentação.